Testing, 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 testing. Testing. All right, we're live. Welcome to another Hoopo stream. Got some upgrades on the video stuff. We're basically doing separate computers now. So the stream you see is actually coming from a Windows desktop. And then I have my Linux desktop being basically piped in with a VNC server. So hopefully that reduces some of the weird audio lag that you guys were seeing, where basically if I would run a machine learning model at the same time as trying to stream, it would like mess with the audio. So now we have separate computers for streaming and a separate computer for development, which is what I'm doing here. So, man and a cat, yep. All right, so let's catch up on what we're doing here. We had a Vesuvius challenge, trying to detect ink. We've been training some models, and we ran a bunch of models overnight. So this right here, you guys see, this is all the models that we ran. So you can see that we started this training run around 3 p.m. And then basically now it is now 9 a.m. So every single one of these lines is a different machine learning model that we trained. You can see that some of them have the zigzag. The ones which have the zigzag are the ones that were trained with a curriculum, which means they were trained with multiple data sets, kind of alternating different data sets. And yeah, you can see some of them are fast, some of them are slow, some of them didn't really learn. This one here didn't really learn anything. This one over here, this orange one, kind of learned the best. So that's the one that I want to check out, this orange one. So I can go to the orange one. Let's actually go into the output. Each of these folders is one of those lines. And this orange one here, I can look, and the UUID for this is 295FD. So then I can just search here for 295FD, which is this one. Open that up. Look at that, guys. Look at that. We are predicting. We are making accurate predictions. This is beautiful. Love to see it. This is the test data set. So this is the only thing we have is the mask. That does seem like it fits inside the mask. That model seems to be the best. So let's also look at this gray model. I'm interested in this gray model, C6388. Go into output, train, C6388. All right, let's check it out. And this is the one that was curriculum learned. Okay, so this one is actually also doing a little bit of learning too. It's not quite as good as this one here, but it's close. So what do these two have in common? I think that's the next question we want to answer, is what do this gray one and this orange one have in common? And specifically because we were sweeping. So if we actually, let's close out. Don't need to be training anymore. Kill that. Let's open up here. This is the sweeps that we were doing. So we sweeped over a couple different things. We sweeped over the optimizer, sweeped over the model choice, we sweeped over the curriculum, and the number of samples. So let's come over here and let's compare. So let's do this, and let's filter these runs by the ones that used the normalized form of the SimpleNet network, and then the ones that used the non-normalized SimpleNet form. So Okay, it doesn't look like the normalized ones did well, to be honest. Simple, net, simple net, num versus simple net norm. Let's put this in step form because I think it's easier to see. So it. All right, it's kind of hard to say which one did better. Let's look at Atom. So these are all the ones that used Atom optimization versus SGD. Okay, you see that both of the ones that did well, which is this orange one here and then this gray one here, both of them had Atom optimization. So I'm kind of liking the Atom optimizer. Let's go ahead and open up our README. Let's say sweep number 2 results. Best results. So optimizer equals Atom. What else? Curriculum. So we had 1, 2, 3. These all kind of did terribly. We had 3, 2, 1. 3, 2, 1 did okay, and then we had 1. Sorry. Curriculum 1. Curriculum 2. Curriculum 3. Okay, so 2 is actually the worst. Really, it's the one that had 3, 2, 1, and then 1. So curriculum 3, 2, 1, and 1 were the ones that did well. Let's see, what else? So let's get rid of this one too. That. Simple image augs, image augmentation. See if that changed at all. Image aug. True. Image augs. There we go. Okay, so the true versus the false. Okay, so actually, it looks like the image aug false actually did better, which is actually not intuitive, right? You would think that with image augmentation, you would get better results, but image augs false. Sometimes the results you get on machine learning is not intuitive. Sometimes things you think will make things better will actually make things worse, and things you think will make things worse actually make things better. Make a roadmap video for beginners who want to get into machine learning. What type of machine learning do you want to do, Ankit? Okay, so image augs. This actually does better if you do false, so let's comment that out. And max samples per data set. All right, let's compare the 2,000 versus 8,000. So these are the ones that had 2,000. samples per data set, and these are the ones that had 8,000 per data set. All right. So I think that's the difference right there. You can see here the difference between the ones that had 2,000 size data sets, or 20,000, sorry, and 80,000. So all the ones that did well had 80,000. And that one actually does make a ton of sense, right? What was the name of this parameter? Max samples per data set. 8,000 did better. Okay. So, a couple different things we want to do today. So one thing that we could do is I didn't like how the zigzag happens. So I think one thing we want to do here is here where we're actually training, so we add the loss name. I think here we need to also add the data set itself. So, right, because you see how this zigzags, that means that the loss for the different data sets is actually different, or is a different value, and it makes the zigzag, makes it hard to read. So the way that we're going to do that is we're actually going to use the current dataset ID inside the name of the scalar that we log to TensorBoard, like that. And that'll give us 3 different plots, and those 3 different plots will be easier to understand. I don't know, I just learning stuff without knowing where to go next. Yeah, I mean, just let your curiosity kind of guide you. There's not, I think a lot of people who start with machine learning, they think that there's some path to expertise that is shorter than all the others. Right, but that's not the case. There isn't like some secret. It just comes down to time, right? It's like anything else in life, where it's not like Arnold Schwarzenegger knew some kind of secret and that he knew exactly how to work out, and if you just worked out like Arnold Schwarzenegger, you'd look huge in a month, right? It's not the case. Arnold Schwarzenegger is huge because he worked out for literally 20 years, right? So it's the same thing with machine learning. It's like you don't need to worry too much about kind of your curriculum, right? The classes, the books, the stuff, like don't worry too much about the right books, the right things. Anything you do will make you smarter, right? So do a Kaggle competition, go on Papers with Code, right? Find a cool paper that you look and you're like, oh wow, that's an awesome paper, and then click it and try to read it, and you're probably not going to understand all of it, but you'll understand some of it, and then over time you'll understand more. So find something that you think is interesting and then just spend time. And more important is the interestingness, right? Because at the end of the day, it's going to come down to time. So if you do things that are interesting to you, you'll spend more time. If you do things that are not interesting to you, you're not going to spend more time. So do the things that are interesting to you. Yeah, there's so many resources online. Okay. Where were we going? Okay, competition, memory is real. Pre-trained weights. Okay, yeah, so this is something I was reading yesterday, and it has me completely changed. So you can create 2 notebooks, one for training, which you turn on the internet and download. After training, save the model and load it in another separate notebook for predictions and submissions without the internet. Okay. So this is changing me, because up until now, I thought that you needed to have, you couldn't basically download any pre-trained models because your notebook can't access the internet. So anything you use has to be basically built from scratch, which is what we did here, right? We in this competition, we're not using a pre-trained model. We're basically just we're just using a neural network that we make from scratch here, and then we're just training it from scratch, right? And generally, you don't really want to do that because it's actually very inefficient to train a neural network from scratch. You want to basically use a pre-trained neural network. But the way that this competition made it sound like you basically need to make one from scratch, which isn't great. But it sounds like you can actually like create a notebook that has access to the internet, download a pre-trained model, and then the submission notebook itself is not connected to the internet. So I'm going to see if I can figure out how to do that. Download the pre-trained weights and add it to your kernel. I think if we go here and we go to competition, go to the Vesuvius challenge. Let's make a new notebook here. And what we're going to be using is one of these. So this right here, these are pre-trained models that PyTorch gives you. So these are pretty good pre-trained models. You have everything. You have vision transformers, you have ResNets, you have mobile nets, you have convnexts. Like, you have pretty much every single type of pre-trained vision model that you want, right? And they're all pre-trained, which means that they've been trained on these big data sets. And ideally, you want to take one of these and fine-tune it for this task. So what we're going to try to do here is we're going to try to see if we can make a notebook that downloads this model, right? And I think what you have to do is add data. So really what this is changing is that now the notebook that we use only has to be basically fine-tune an already pre-trained model. So I'm going to try to take, for example, this right here. So video data is kind of probably what we want because the data that we're doing for this competition is a 3D file, right? At the end of the day, if we look at our files, not Flameshot, files, right? We have our home, dev, Ash and Venus, data, train, right? This is basically almost like a video if you want to think about it, right? Video is height by width by channels by time. And here we have height by width by depth, right? So you can't use a pre-trained model that only has 3 channel dimensions. You're going to have to use something that's got more. And one way to do that is weight inflation is what they call it. But basically you take a pre-trained model and then you duplicate the weights along the depth axis, and that allows you to use a pre-trained model with something that's larger. So I am going to take the largest quantized model. I don't want that. I want classification, convnext tiny. This is what I want here. Accuracy 28, 26 mil parameters. convnext large. Let's just try it with the convnext tiny. So go into our notebook areas here. We're going to save. Let's actually save the stuff here. This sleep var commits clean. And let's make a new notebook. New file. We're going to call it 07 and we're going to call it pre-trained .ipynb. All right. Here we're going to basically copy paste this. And we don't want ResNet 50. We want convnext tiny. Let's see, convnext models dot, it's not segmentation, on models dot classification. Torch vision models, and we want convnext. Side convnext. Have convnext tiny. Convnext tiny width. Yeah, math is important. I agree. You can definitely learn math, and math will always be useful for pretty much anything you do. Here on convnext weights. Okay. So this is where it actually downloads it. Model load state dict. Tiny. Let's see if we can even get this to start a new kernel here. Okay, so it downloaded it, and you can see that it put it here. Home, friend, cache. So it downloaded it to this. You can actually go into that. So if we go to like open this. Home. Show hidden folders. Show hidden files. .cache. Torch. Hub. Checkpoints. And convnext tiny here. Okay, so let's copy this. Let's put it in path right here. So we're going to put it inside our notebooks folder. .pth. So let's also add it to our gitignore. So our gitignore is a file in our GitHub GitHub repo that tells GitHub which files it shouldn't commit. So we don't want to commit a pre-trained model. So model weights okay, so now we go there, it should be okay. So we've added it to our git ignore. Now I want to be able to load these weights from a local file. So I think what we need to do, convnext tiny weights weights verify URL load state dict from URL. PyTorch load pre-trained weights from local path. Alls, as I understand, is that model class. What is this? If I do this, what if I copy this, come here, put this here, hot, or do we just need to copy this? What if we do this here? Initialize with weight. Basically going to create a weights object. What is this weights object? Can I tell it? URL, location, where to find the callable that constructs the pre-processing, or so maybe we don't actually need to copy paste all of this. All we need to do is convnext tiny weights dot default and then say weights dot URL and put in the path of our thing. So the path of our thing is going to be this properties notebooks of next. All right, and let's see if this actually works here. Can we load the weights from a local path here? Can't set attribute. Can't set URL. That's not. Waits. URL. Other. Turn self.value.url. I do self.value.url like. Ooh, look at that. All right. It looks like we can load them from a local path. So what we're going to do here is in our little fake notebook here, we're going to come here and we're going to upload some data. And the data that we're going to upload is going to be add data. And just like upload a file here. Upo, what's up? Sorry, Saigi, I'm not like paying attention to the chat. Is there something I can help with? ImageNet as in conv next. Cancel. And the file we want to upload is this one, conv next tiny. Pre-trained fast AI model weights. I don't know. Include duplicates. Okay, close. Okay. Now copy this. Put it here. What is the path to the copy file path? Put it here. And what we really want to do is turn off the internet. And then see if it works. Okay, it's going. Right? Oh no. Unknown URL type, Kaggle input cognet. Fuck. Theo, Vision. Have any models here? Maybe I need to change this get state tick from URL into load state tick from URL. Is there a load state dict? PyTorch save for open model weights from path rather than URL. Unable to load weights, saving loading models. Model state dict, path. Maybe you can do this. So our model is that conf next tiny. And then we're going to load the path to pre-trained weights. File path. Name torch is not defined, actually. Torch. Pre-trained weights file path is not defined. This. Oh shit, we did it, guys. Look at that. All right, perfect. Okay, so it seems like we can basically use a pre-trained model and we can load the weights and we can use it in an offline notebook, which means that we're going to actually pivot here. We're going to stop trying to make our own little machine learning model and training it from scratch. We're basically going to take a pre-trained model, and now the problem is, rather than training it from scratch, we're going to try to figure out how to fine-tune this for this task. And fine-tuning is different than training from scratch. Training from scratch, there's a lot of different tricks you want to use. Training or fine-tuning, a whole bunch of different tricks, right? So here is roughly what I want to do. I found this paper. This is a relatively recent paper. Adapting pre-trained vision transformers from 2D to 3D through weight inflation improves medical image segmentation. Medical image segmentation is actually very, very similar to what we're trying to do here, right? What we're trying to do here is scroll classification, but the scroll is also a 3D data format, right? So large-scale pre-trained transformers are used as the encoder in the segmentation model for transfer learning, in which the weights are adapted using the inflation strategy to support 3D inputs. Each 3D image is split into windows, which contain a small number of neighbor slices. Each window is fed into the segmentation, and the segmentation of the center slice is predicted. Okay. So we're going to be doing the same kind of weight inflation. However, I'm going to pause this for a second. I need to think real quick. Alrighty. Sorry about that. I had to deal with some real life things. But we are back. All right. So this is the convnext tiny, right? And there's a couple different things that are no good here, right? The first thing that is no good here is that the very last layer here is no good for us, right? We want a 1D classification head on top of that, right? And then we also want the input to be different, right? Because the input size is going to change. The number of channels is going to be different, right? So here you see it's a 2D convolution. The input channels here is 3 versus we're going to want 65 input channels. So we're going to have to inflate the first layer here. And we're going to have to add an additional head, or potentially remove this head. Average inflation, centering inflation. Okay, so if we actually look at the code here, model, let's look for centering. Twin transformer. Whether to inflate or center the weights. Go here. Load state dict. Load a checkpoint. Number of slices, number of channels. Patch embed projection weight. Here's the actual centering. Relative position bias, reshape absolute precision embedding. Then he puts a little multi-layer perceptron. This guy's doing a little bit, this is a little bit unnecessarily tricky here. Let's actually look at this paper, see what's going on. Large-scale pre-trained or uses the encoder in the segmentation model for transfer learning, in which the weights are adapted using the inflation strategy to support 3D inputs. Each 3D image is split into windows which contain a small number of neighbor slices. Each window is fed into the segmentation model, and the segmentation of the center slices is predicted. All the predicted slices are aggregated to form the final 3D prediction. Weight inflation on a pre-trained weight inflation for pre-trained model PyTorch. Maybe, what if we just wrap our model into this? Right? What if we make a model that takes in the 65 channels, uses a convolution to turn it into 3 channels, and then uses that pre-trained model to basically act as an intermediate. Can we do that? Get the model's input layer. Model's output layer. Model's input layer, wait 10 seconds. I don't know what Cat or what Copilot is trying to get us. Next is no. We save here. Go into our model actually. Control P dot pi. Let's get our little simple net here. Come here. Add that there. We're going to copy paste our utilities. Let's run it. And here, we're going to do this. We can actually do this. Be pretty Frankenstein, but use pre-trained model. Pre-train net. Pre-trained weights file path. And let's put all this here. Self.model, self.model. What kernel size do we conv2? 3x3 probably is the best one. Then FC1. Let's do FC and conv. Let's just call them that. And here, first thing we're going to do is feed it through the conv. Then we are going to feed it through the model. And then we're going to feed that through the. So we run that. And we try to create a version of this model. Model pre-trained net. The pre-trained weights file path. Just leave this, and we will put shape here, output shape. Output shape. Here. Basically make a fake tensor of size input shape. I'm pretty sure conv next requires a specific size. Images are resized to 236 followed by a central crop of 224. Try 224 by 220. And we'll create that X and we'll make the Y runs. File not found. No such file or directory. Oh, not. You want train weights equals dash home dash trend dash dev dash this dash notebooks dash comics. All right, and then what is Y? Y is 32 by 1. That. Damn. All right, guys, we're gonna be crazy. Because we basically now don't need any, you can just use these pre-trained models. All right. So come here. Actually, before we do that, let's also try it out on the Kaggle notebook. Add that. Works. Works. So here. Now we're going to go to our model. Let's this binary CNN classifier and this. We don't need any of this garbage. And let's put in our torch vision models. And we're going to import a couple different things. We're going to import convex tiny. Let's see what else we can import. I think we should try at least one vision transformer. So I'm looking at the accuracy here and the number of parameters. So VITL. VITB on here. Weights ImageNet 1K, ImageNet 1K VITL. How about this one? This one is kind of small. So models VITB32. VITB32 and then VITB32 weights. And let's get like one ResNet in there. Let's get the ResNet, this one here, ResNet ImageNet 1K V2. ResNet 152. Net 152. And ResNet 152. All right. So we have 3 different pre-trained models now that we can use. Let's go into our pre-trained net here. Add this. You don't really need the pre-trained weights file path right now, so let's comment that out. What we do need though is a pre-trained model, which is going to be string and convex tiny. That's binary classification on top. here we're going to say load pre-trained model. If pre-trained model is convex tiny. Yep. If B32. Yep. If ResNet 152. Yep. Dot default. About this one. Default. Default. All right, so now we have our pre-trained net with 3 different pre-trained models. Binary classification head. Else seems fine. Let's go into our train code. We're going to add code here. Go back to our model. We can make copy. Model equals. We're going to have to import pre-train here. Copy paste that pre-trained net, put it here. Slice depth and model name actually called. And the same. Okay, so we've added our 3 models to this. And let's go ahead and add it to our hyperparameters as well. So go to heap, we add our 3 hyperparameters here. We don't really care about simple net. Also try the SGD in case one of these pre-trained models does better. Okay. And I also wanted to add learning rate scheduler PyTorch. Using learning rate scheduling in PyTorch. Torch optim LR scheduler. Add that. Here, torch optim learning rate scheduler. Let's import the matplotlib. LR schedule, linear learning rate, start factor, end factor, total iterations 10. Binary cross entropy, LR equals LR. Doesn't have any learning rate scheduling. Here we go. Scheduler, LR scheduler, optimizer. And then scheduler dot step. So let's add a LR scheduling. And we'll here in optimizer, we'll say if step LR. What other types of learning rate schedulers? Lambda, step, multi-step, constant, linear. Let's ask ChatGPT. Chat. Hi. What's going on? Global rate limit exceeded. Best learning rate scheduler for fine-tuning. Neptune.ai 2021. Let's see. I think this is just like we want the article that we were clicking. I guess which one do they use? They use linear LR. Learning rate takes 3 additional. The start factor, end factor. You can set start factor to 1, end factor to 0.5. It will make multiplicative factor decrease from 1.0 to 0.5 in 10 equal steps. After 10 steps, the factor will stay at 0.5. You can use exponential LR. Yeah, this one actually seems exponential LR. Exponential LR. Gamma 0.9 and take this scheduler, and I think all you have to do here's say scheduler.step. So after each epoch, which is basically here, So it trains on that one data set. We're going to come here and we're going to say if learning rate scheduling, scheduler.step. Actually copy this bit here because it's okay. And instead of this, why don't we make this a and done, and then say LR schedule gamma. Name this LR schedule gamma. Then we say if LR scheduling gamma is not none, LR schedule. If LR scheduling gamma is none, and in our sweep pass LR scheduling gamma. Here, create a new hyperparameter called LR scheduling gamma, and the choices for this are, let's say 0.1, 0.9, none. Okay, so we have our stuff. So before I'm gonna delete the stuff in this folder. But before I do that, let me get the one that was not this one. Get the name of this folder. Put that there. Save it. Okay. So now that like trash these. Go here. Remove -rf output star. So we're going to clear all the data. Now we're going to run the sweep. All right, expected state like dict got enum conv next tiny weights. So because we don't want to use this code stick of pre-file path, and then this part here actually has to be more like the examples is like this, and then you weights equals. Let's multi-cursor our way to success here. Say weights equals okay. Now let's go back and run it again. Let's run it with a seed of, what was our testing? 420. Out of memory error. $224 by $224 with a batch size of 32. Try that. All right, and it's training. We don't actually care about this prediction. Let's actually close out of that. Go back to our train. And let's not evaluate. And let's run it again. And let's look at our tensor board. I think we might have to do self.model. Whether to set training mode true or evaluation mode. Let's put model in mode. CUDA out of memory. Not looking good, dude. These models are big. Models are big. Model. Actually, trained. Okay, I mean, these are some of the smaller models that I feel like I can get. Oh no, it's the ResNet 152. I feel like maybe that's just way too big of a model. Let's see if we can find a smaller ResNet. So, the ConvNext Tiny has 28 parameters. Can we like sort this by parameters? Can we find one that has roughly less than 28 parameters, a ResNet with less than 28 parameters, 28 mil? ResNext 88 mil, ResNext here 25 mil. This one. ResNext. Try this one. And we'll this. And then okay, let's try that. Let's check this VIT-B32 because this one's probably also going to be too big. Yeah, 88 mil parameters. Is there a VIT that has less than that? That's literally the smallest one is 88 mil. That's not good. We might not be able to get a VIT that is small enough to fit. What about this one? Swin T transformer. This one only has 23 mil or 28 mil parameters. Let's do that one. Swin. And Swin T weights. Okay. And let's go to our train. Add our add it to our sweep. Let's comment out this one because it's big, and then we'll. All right. Right. Here's the ResNet. ResNet seems to be training fine. Here is the SwinT. Which one is this? Yeah, this is the SwinT. The SwinT also seems to be training fine. How much memory are we using? Damn, that's like pretty much the full memory right there. I think if we increase the depth of the slices, it might boom on us. ConvNet tiny. Also huge. Like, look at this. Okay. Let's look at our logging, see how that's going. This is good. This is like the 3 different brain losses. Loss goes down. They're weird. Some of these loss goes up. Pretty much for all of these, the loss goes up. So here's the thing. I don't know if let's do freeze a backbone true or false. Optimizer model freeze backbone. Add the freeze backbone parameter. Add the freeze backbone parameter. Freeze backbone equals backbone. And here, if we get a freeze backbone of false, if freeze backbone pre-trained model dot eval, else model true. Okay, so now we're going to optionally freeze or unfreeze. And I think when we actually do evaluation, evaluate model to device, and also let's do model dot eval to put it in eval mode. Let's commit this. Let's say pre-trained models. Sync. And we're going to run this. Try. File name too long. We officially ran out. Let's get rid of patch size, image og, some epochs. The only thing we really care about is curriculum, model, freeze backbone, optimizer, learning rate gamma, and max sample data. Let's try it. Let's try it. All right, so now it's loading the Convex Tiny training. Now we should also yeah, I just feel like the problem is that the memory is so huge. You see this? We're already like almost at capacity here for the GPU memory. So let me kill this. Let me remove the output. Let me try with the full slice depth. And just do 2 batches. I want to see if the slice depth causes out of memory. Okay, so Convex Tiny does not cause out of memory. It can quite successfully train. You know what the problem here is I don't actually give a shit about the curriculum. So let me get rid of this for now. Let me just do curriculum 1. Let's remove the output. Let's try it again. Context tiny. Epoch 2. What is this? This is res next. Res next seems to work fine. What is this? Swin T. Swin T also works good. Okay. Swin T is actually pretty close to max GPU memory, but it is fine. It is working. Okay. So this is looking good. We have all of our models seem to be okay. So let's put the curriculum back in. Let's do 3, 2, 1, 1, 2, 3. Learning rate, let's kind of crank this down a little bit to 0.01 all the way to 0.001. Just because we're fine tuning, so I think using a smaller learning rate makes sense. 65 num workers, max samples per data set 80,000, slice depth 65, resize ratio 5, resize ratio 2.5. Num epochs 6. Yeah, fine. Okay. I think we are done here for today. We just need to remove all the logs. Let's make sure these logs are done. Then let's commit this. Ready for sweep number or sweep 3. Okay, so what are we going to be sweeping over tonight? And we're going to come back tomorrow morning and we're going to look at our stream and then we're going to see what we did. But the experiment that we're running tonight is we're going to be comparing a curriculum of just the training dataset 1 versus a curriculum of 1, 2, 3, and 3, 2, 1, which is training on dataset 3, then training on dataset 2, and then training on dataset 1. We're going to compare our SimpleNet with ConvNext Tiny, Swin T, and ResNext 50. We're going to compare whether or not you freeze the pre-trained model. We're going to compare the optimizer from Atom and SGD, and we're going to compare learning rate scheduling gammas. And one thing we can actually do here is we do this. Try accept pass. There we go. Loss equals 1 million. So now if there's any weird error that we didn't run into, it'll trigger this exception and it'll just keep going. Let's also make sure to uncomment our evaluate line so that we can actually see visualizations. All right, let's commit that again. try catch. Run that. Close some of these. All right. Move the outputs and let's do seed 23. And here seed 75. All right. So we have both our GPUs blasting. We're looking at the memory here, so this number over here, looking fine. And we're looking good. So now I'm just going to put this away, and then I will come back to this tomorrow, and we will see what we got. Thanks for listening so far, and let's hope that we can find something cool tomorrow. All right, see you guys later.